Welcome back all of you. Since last 1 or 2 classes, we started discussing about solid state NMR. I briefly introduced to you what are the interaction parameters that are present in solid which gets averaged out in solution state. For example, dipolar couplings, both homonuclear and heteronuclear, chemical shift anisotropy, J anisotropy, all these parameters are averaged out in solution state, but they are present in the solid state in its full form. I said full form because it can be also reduced by doping the molecule in a partially ordered environment, that is what I said, in some liquid crystals. But anyway, in solids, because the order parameter is 1, it is fully present and it complicates the NMR spectrum a lot. And why it complicates the NMR spectrum, that is what we discussed. Because all these parameters are orientation dependent, it depends upon a factor called 3 cos squared theta minus 1 by 2, where theta is the angle that the internuclear vector makes with respect to the magnetic field as far as the dipolar interactions are concerned. If you go to chemical shift anisotropy, I said the charge distribution at this site can be considered like an ellipsoid. It depends upon the orientation of the ellipsoid, direction of the ellipsoid, that is also orientation dependent. It depends upon 3 cos squared theta minus 1 by 2. As a consequence, I said this also depends upon 3 cos squared theta minus 1 by 2. And then I also said, if I gave an example to see that what happens if I vary the theta in case of dipolar couplings. We kept on varying the angle theta from parallel orientation to perpendicular orientation for a given internuclear vector. We found that doublet component alpha and beta, the doublet separation was quite large, kept on reducing at a particular angle, both of them collapsed and then started increasing again. So, this is what we observed, and a particular angle it collapsed, it went to a singlet, and all possible infinite type of orientations are present in a given molecule in a powder form. There are infinite microcrystallines possible, varieties of orientation of internuclear vectors are there. As a consequence, several spectra will be present with the overlap. As a consequence, you are going to get what is called a powder pattern, that is what I said. Same thing in the case of chemical shift anisotropy also. Depending upon the orientation of the ellipsoid, which then the chemical shift for a particular molecule can keep on varying, the position keeps on changing. And I took the example for 3 possible orientations for one of the molecules. I showed how the chemical shift changes, because again it has infinite possible orientations, the overlap of them gives us a powder pattern. We saw 2 types of powder pattern for chemical shift anisotropy. One is axially symmetric, other is axially asymmetric. In the axially asymmetric pattern we clearly saw we have sigma 11, sigma 22, sigma 33. These are the principal components of the chemical shift anisotropy tensor, which is obtained after transformation into a frame of reference where we get only 3 diagonal elements of the CSA. That is what we thought. For axially symmetric, again we have only 2, sigma 11 are equal to sigma 22 and another is different. 2 of them are equal and third one is different. We discussed all those things, and I said I gave an expression called dij equal to 1 over rij cube into space part into spin part. I said rij is the internuclear distance, all these 3 factors are products, they multiply among themselves. Then I said rij can become infinity when we consider 2 spins which are dilute, because their probability of finding both of them, for example carbon 13 in carbon 13 state is 1 in 10,000. As a consequence, we can say these dilute spins are infinitely distance separated out, separated by infinite distance. So, Rij becomes infinity, the dipolar coupling becomes 0, or in other words we can say for dilute spins the dipolar coupling probability of seeing is very, very low. Now, we discuss about the space part and the spin part. Using these things we can also average out, that is what we said. Space part is the rotation of the sample at a given angle at a particular speed or some speed. Then I said second order interaction tensors like heteronuclear dipolar coupling, CSA, everything will get averaged out. In the spins part we can also do the same thing by making the spins to go through all sorts of similar rotation in the spin space, and we can average out some type of dipolar coupling, homonuclear dipolar coupling. I said that. Today we will go further detail and try to understand what is magic angle spinning. Okay. Now I will tell you what is a magic angle spinning. Magic angle spinning is what you will do is take a sample, put it in a rotor like this of length about let us say 1 to 1.2 centimeters with inner diameter which is varying from 7 mm to 4 mm to 2.5, 3 varieties of dimensions diameters you can have. Put the sample into this, align this rotor, axis of rotation of this rotor with respect to certain angle with respect to the magnetic field called magic angle, which is 54.7 degrees. Why this 54.7 comes? Put it into the equation 3 cos square theta minus 1 by 2. Okay. Then you will find out at the angle 54.7 this term goes to 0. That is why this angle is called a magic angle. Align this rotor at that particular angle and then start spinning at certain speed, then you can eliminate some interaction. This is called magic angle spinning. And how do we do that? By using the compressed air at high pressure air. So, we are using bearing and driving pressure, we adjust the spinning speed to make the sample rotate at certain spinning speed of the order of several kilohertz. Okay. So, rapid spinning of the sample about the magic angle, what it does? It removes heteronuclear dipolar interactions, heteronuclear dipolar couplings, and any other second rank interaction tensor which are present, they also will be removed, and CSA also will be removed. Just to show you a typical sample holder for magic angle spinning, this is like this is a rotor, and if you take a NMR tube for the solution state, it will be like this, a 5 millimeter rotor of length about like 10 to 12 centimeters and inner diameter is about 5 millimeter or sometimes 3 millimeter also are there. But in the case of solid state, since you have to rotate the sample at a rapid speed, the sample is taken a container like this called rotors. It can vary diameter, internal diameter from 4 mm to varieties of sizes, which I am going to show you as we go ahead. And there will be a cap, we have caps of what are called flutes like this, and then using these flutes what we do is we will rotate the sample at a high speed and we will put a marker here at the side, so that we can measure the spinning speed. So, all these things are little details, but do not worry, this is the I wanted to get you the feeling what is the where how do you use what is we put the sample in a particular material called rotor, how does it look. Okay. And varieties of rotor sizes are available, so you will find 7 millimeter mm to 40, even 14 mm are also there. 7 mm rotors we can consider, these are all the rotors of varieties of sizes are there. Okay. And then spinning speed depends upon this inner diameter of the rotor. You can look at this is 7 millimeter rotor which is taken from Physics Today October 2016. This can give you spinning speed up to 8 kilohertz. If you go to 4 mm rotors, you can go up to 15 kilohertz. Go to 3.0 mm rotor up to 23 kilohertz you can go. 2.5 mm rotor you can go up to 35 kilohertz. If you go to 1.3 mm you can go to 60 kilohertz, and 0.7 mm can go up to 111 kilohertz. Now, attempts are there to increase the speed even further. So, you understand, look at the size of this rotor, it is very small, 0.7 millimeter inner diameter within which you have to put the sample, and how much sample quantity you put it in. For example, if you take a 1.3 millimeter diameter rotor, you can put only 2 microliter sample, that is enough. You can look at the size of the quantity of the sample that you are utilizing. One advantage is you can go to high spinning speed, that has a lot of advantages I will discuss as we go further, but sample quantity is less. So, signal to noise ratio there is a compromise since quantity of the sample is less. On the other hand, go to let us say 40 millimeter diameter rotor, you can give spin at maximum of 5 kilohertz, but you can take sample of 1 to 3 ml. You have very good signal to noise ratio because sensitivity you can enhance a lot because of the sample quantity. So, there is a compromise on all those things. I want you to understand, as the size of the rotor increases, the spinning speed increases, but the sample quantity decreases. So, there is a compromise you have to work out depending upon what you require. This is inner view of a magic angle spinning probe. This is different from the conventional liquid state probe. This is where we are going to house, this is where rotor is going to sit, this is called a stator, and the rotor goes and sits inside this. There is a small diameter appropriate to the size of the rotor, you have appropriate probe. This is, let us say, about 2.5 mm rotor, it goes and sits into this. This is the inner view of it. And then what is so magic about the magic angle? Okay, I have put the sample in a rotor, put the rotor in a aligned at an angle with respect to magnetic field and start spinning at some rapid speed, some speed 20, 30 kilohertz, whatever the speed I can achieve in a particular rotor. Then what is going to happen? Look at it. If you look at it, different internuclear vectors are there which can make different angles with respect to magnetic field. Before spinning, you understand. You take a rotor and put the sample in this, innumerable number of internuclear vectors you can see, because in a powder sample varieties of orientations are possible. You have simply stuffed the rotor sample into this rotor. Now I can consider internuclear vector between 3 and 4, let us say, that is the internuclear vector 3 and 4 here, and this is making certain angle with respect to magnetic field, and another internuclear vector here 1, 2 is making different angle. But like that, infinite angles, infinite internuclear vector, each of them may be making different angles with respect to the magnetic field. Then what is going to happen is, if I consider a static situation, I do not spin the sample at all, then I come across a situation, this theta 1, 2 angle between internuclear vector 1 and 2 with magnetic field is not equal to theta 3, 4, correct. If you put the sample, different internuclear vectors are there with making different angles with respect to magnetic field. But on the other hand, when I start rotating the sample, what is going to happen is, the time average, ensemble average is such that the average orientation, if you consider for this type of internuclear vector theta 1, 2 or any internuclear vector theta 3, 4, anything you consider, all internuclear vectors, it appears as if they all aligned along the direction of the spinning axis. This makes 54.7 degree with respect to the magnetic field. That means you have artificially created a situation by spinning the sample rapidly, all internuclear vectors are aligned along the direction of axis of the spinning, which makes an angle 54.7 degree with respect to magnetic field. All internuclear vectors you can assume are along this internuclear vector, along this spinning axis, which makes 54.7 degree. So for chemical sheet anisotropy, magic angle spinning, all of them, the average long axis of an ellipsoid now aligned along the spinning axis. If you consider CSA, you have an ellipsoid, the average long axis of the ellipsoid or internuclear vector for in the case of dipolar coupling, all of them you can deem it to be aligned along magic angle. So if you consider the average orientation, the magnetization under magic angle spinning, let us consider a cuboid. I have a cuboid 1 into 1, 1, 1, which is the direction of this cuboid here, which makes angle with body diagonal of the cuboid. This body diagonal of the cuboid, along this, you imagine in the drawing, this is the angle body diagonal makes with respect to magnetic field, which is theta m, which is nothing but the magic angle. It is a cuboid, okay, 1, 1, 1, and find out the body diagonal of it and find out what is the angle it makes with respect to the magnetic field, which is along z axis. Then you find out it is 54.7 degree. That is what happens. The rapid spinning of the sample about this axis removes all dipole interaction and all second order interaction tensors, okay, when you are spinning at this angle. So what do you mean by this? If you have to understand this, it means magic angle spinning can be treated as a dynamic implementation of the cubic symmetry. What do you in the previous cuboid, it is a cubic symmetry is there, and then if you start spinning the sample rapidly, you can imagine all the internuclear vectors or the long axis of the ellipsoid in case of CSA, they are all aligned along the body diagonal of the cuboid, which makes magic angle 54.7 degree with respect to magnetic field or the z axis, spinning axis. Now what happens if I spin at different speeds? I need to have certain spinning speed, I will come to that later. Supposing I have a very slow spinning, I showed you several examples. I have a rotor spinning at 5 kilohertz, 10 kilohertz, for 30 kilohertz, 60 or 100 kilohertz, like that. If I start spinning at a slow spinning speed, then what is going to happen is the precision in NMR frequency gets modulated by the rotor spinning frequency. It interferes. NMR precision frequency, it gets modulated by the rotor spinning frequency. By this equation I did not go into the details, do not worry, it gets modulated. Okay. And contributions from different orientations of the refocus at each rotation and tower, which is called rotary echoes. Okay. Rotary echoes are the ones which in which different orientations refocus after each rotation, and as a consequence we get spinning sidebands separated by rotary spinning frequency from the in the spectrum. What I mean is, supposing if this is a peak I am supposed to get, now I start spinning at a slow speed at a spinning speed nu r. Okay. Then at exactly integral multiples of spinning frequency I am going to get what are called side bands. These are called spinning side bands. Spinning side bands will be at the frequency of the spinning speed at which you are rotating the sample. Okay. Take for example, look at this example. The free induction decay, this is collected by spinning the sample only at 1.25 kilohertz. What are these things you are getting? It is at the frequency domain spectrum. It is a time domain signal. These are all called rotary echoes. What each 1 hour tower you are going to see this type of refocusing. And if you do the Fourier transformation of this time domain signal, you get a frequency domain signal like this, frequency domain spectrum. Now you measure the separation of any of them, this corresponds to spinning frequency. Okay. This is what it is. These are called spinning side bands, which comes at exactly integral multiples of the spinning speed. Now you may ask me, where is my peak from my sample? We will come to that later. If this is your sample, with respect to that you can find out all the side bands are separated on either side by spinning speed, integral multiples of spinning speed like omega nu r, 2 nu r, 3 nu r, similarly minus nu r, minus 2 nu r, like that. Okay. So magic angle, how do you set it then? It has to be extremely precise. Remember, slight deviation from the magic angle, you are bringing in the dipolar coupling or other anisotropic interactions. What normally is done is, we take the bromine resonance of potassium bromide and look at the rotary echoes. This is what I just now explained to you. These are called rotary echoes. Do not spin at a very high speed, spin at certain normal speed, normal rotation frequency, spinning frequency like 4 kilohertz or 3 kilohertz or 5 kilohertz, and start looking at the rotary echoes like this. Then you can start varying the angle in the probe, magic angle. There is a way you can vary there is a probability, not there is a provision for you to change the angle, keep on changing. If the number of rotary echoes what you see are very much less, that means you are off magic angle. You keep on tuning such that you get more number of rotary echoes like this. Then more the number of rotary echoes, you are getting into a more accurate magic angle. You are coming very close to magic angle. That is what it is. So bromine resonance of the potassium bromide, if it is taken and we set the magic angle, this is how the spectrum comes. This is the central frequency corresponding to bromine 79 resonance of potassium bromide, and these are all side bands. Okay. Larger the numbers of side bands, then you are more accurate with respect to spinning speed. If these side bands only few are left are there when you are spinning at a moderate frequency of 3 or 4 kilohertz in the potassium bromide, then you can be rest assured you are very much off from the magic angle. So this is important. When you are close to magic angle in potassium bromide, bromine 79 resonance, you have lot of side bands. How precise has to be magic angle? That can also be understood in a different way. Another sample which is normally used to understand the magic angle setting and also decoupling power, I will come to that later, is the carbon 13 NMR spectrum of hexamethyl benzene. What is CP mass? I will come to that, do not worry. This is by using hexamethyl benzene. You look at the hexamethyl benzene has 2 types of carbons like this. We have CH3s, 6 CH3s and 6 quaternary carbons. So these are all the CH3 peaks, all CH3s are equivalent, and this is a quaternary carbon. There are 2 peaks only, you get 2 carbon peaks. See now when you are exactly at the magic angle, which is 54.7 degree, you are going to get two peaks well resolved. Look at the sharpness. Now, slightly deviate by 0.7 degree, not even 1 degree, 0.7 degree, go to 54 degree, this already distorted this CO peak drastically. This is what we concentrate on the CO peak to set the magic angle precisely also. Okay, I just go 1 or 2 degrees away, this peak completely disappears. It is very sensitive to the magic angle. And just I tell you, move away from the magic angle just by 1 degree, you are bringing in 2.5 kilohertz of the line width into this spectrum. Spectrum so sharp. Now, if you just go 1 degree away from the magic angle, this line width will be 2.5 kilohertz more. That is what happened. So, the magic angle setting is very precise and it is little tricky. So, you have to understand this one. Okay. Next, magic angle, this is the spectrum of a sample, just for understanding purpose I am showing you. This is a fluorine 19 magic angle spinning spectrum of KASF6. You are going to see with magic angle spinning at 5.5 kilohertz, you get 4 peaks. This is where you are going to get fluorine 19, you are going to get couplings with arsenium also. This is where lithium 7 magic angle spinning, and you are going to get this is the molecule, and you see spinning at 20 kilohertz, lots of side bands, you are going to see sharp peaks. If you do not spin it, you get a powder pattern which is like a profile like this. All the top of this side bands or each peak you can join and you generate a broad spectrum, that is a powder pattern. If you do not spin the sample, this is what you are going to get in the static case. But when you start spinning, they break into side bands like this. This is the spectrum of magic angle spinning without side bands. Okay. This is with side bands, here there is no side bands. Another thing is very important thing, what is the effect of high speed magic angle spinning on chemical shift anisotropy? What should be the spinning speed first? And what happens if I spin at the high spinning speed? This is the Hamiltonian. When the spinning speed is larger than the chemical shift anisotropy, I am concentrating on chemical shift part here. When the spinning speed is larger than chemical shift anisotropy, the anisotropic part is averaged to 0 and only isotropic part is retained. If it is not larger than that, what happens? Like we saw in the previous example, we get side bands. The spinning speed should be, especially when you are concentrating on the chemical shift anisotropy, the spinning speed should be larger than chemical shift anisotropy. Only then anisotropic part is averaged out and isotropic part is retained. This is an example of a spectrum of tyrosine, okay, taken from the literature. You see this is a powder pattern without spinning. As soon as you start spinning with magic angle spinning, look at it, how sharp lines you are going to get. Of course, it is no way comparable to liquid state NMR spectrum, where the line width is of the order of 0.2 hertz or 0.1 hertz. But here line width is still quite large, 40 to 50 hertz will be there. But nevertheless, you can see compared to the powder pattern, there are very sharp lines when you start spinning at the magic angle. Here the spinning speed has to be larger than this width of the powder pattern. Only then you will not get into side bands, you get only sharp peaks, which are each peak correspond to chemical shift, individual chemical shift of the particular carbon. So, now with this knowledge, we will understand what is the effect of magic angle spinning on chemical shift anisotropy. Okay. Chemical shift anisotropy in the isotropic part, as I was telling you, it is the average of all the 3 orientations of principal components of CSA, that is sigma 11 plus sigma 22 plus sigma 33 by 3, that is the average orientation, that is isotropic chemical shift. But as I said in the powder pattern, whether it is axially symmetric or asymmetric, all the 3 components are present. In the axially symmetric case 2 are equivalent, but axially asymmetric case all the 3 are different. And this is static sample if you consider. In the isotropic sample, no problem. Or if you take a molecule which has a spherical symmetry, we took the example earlier, you see. When you take the example of a molecule with a spherical symmetry, then it will give a sharp peak even in the static case. That is what we remember We saw that when we were discussing axially symmetric tensor and everything of for CSA. You get sharp peaks. You start doing spinning at the, this is static and start spinning at the magic angle, makes no difference. You get the same little bit reduction in the alignment could be there, but you are going to get same isotropic chemical shift, no change at all. Look at this one, powder pattern which is axially asymmetric. You start spinning at a rate faster than this width of the side band, width of the powder pattern, you are going to get a peak, a single peak, it is somewhere here. This corresponds to isotropic chemical shift of this, and then you get a single peak. Remember, isotropic chemical shift need not be on the exactly on one of the kinks here, like sigma 11, sigma 2 to sigma 33. They are different values. So isotropic shift can be different. Okay. So similarly, sigma for the axially symmetric case, this is the powder pattern, and when you start spinning, this is how you get the spectrum. Okay. So even for chemical shift averaging, similarly, we can do analogous to magic angle spinning. It can be implemented and treated as a dynamic implementation of the cubic symmetry. Again, we saw the cubic symmetry. We understood the body diagonal of it makes 54.7 with respect to the z axis, which is, let us say, along magic angle. We saw for internuclear vector in the dipolar coupling, it is a dynamic implementation of the cubic symmetry. I also mentioned, if you consider the cuboid for the CSA, I am sorry, ellipsoid for the CSA, the long axis ellipsoid can be thought like this, aligned like this, and it is also CSA averaging out can also be treated as dynamic implementation of the cubic symmetry. Okay? That is what it is. So now if you want to see the effect of magic angle spinning and combined chemical shift anisotropy pattern and also heteronuclear dipolar couplings, because in a system they are not two independent parameters, everything would be there. In a molecule you have a CSA, you have heteronuclear dipolar coupling, homonuclear dipolar coupling, varieties of things would be there. Okay. So we will see now in the example like this, what happens in a situation when you have chemical shift anisotropy and heteronuclear dipolar coupling both are present. This is where that sample is spun at 1 kilohertz. You see a lot of sidebands here. So this will be the separation of the sideband frequency, which corresponds to spinning frequency, which is 1 kilohertz. Here the separation is 2 kilohertz, which corresponds to spinning frequency. This separation is 3 kilohertz, this is the spinning frequency. Like that, you come to 10 kilohertz, you do not have any spinning sidebands at all. So what does it mean? As you increase the spinning speed, when the spinning speed goes beyond the CSA or heteronuclear dipolar coupling, then you will not get any side bands. They all merge into central band. That is the isotropic chemical shift. See, you can see only one peak which is not moving, which all the spinning speed. You start spinning the sample at different speeds like this, but every time you can see one interesting thing you must understand, whatever you do, the isotropic peak will not change whatever the spinning speed. See, this is remaining same, whereas the side bands are moving away. This must be remembered. If you want to identify what is your chemical shift, what is isotropic chemical shift frequency, you have to do is, if there are too many side bands, spin at two spinning speeds. The peak which does not move with different spinning speeds is your isotropic chemical shift. All other peaks which keeps moving away with the different spinning speeds, they are the side bands. So this is what you should understand when you take the example of both heteronuclear dipolar couplings and chemical shift anisotropy when they are present. When you start spinning at a rate faster than this heteronuclear interaction strength, dipolar coupling strength or CSA, you are going to get a single peak devoid of all side bands. That is the important thing. Okay. Remember, spinning speed, that is what I am asking the question now, what should be the spinning speed? That is what we discussed now. It should be greater than the magnitude of the anisotropic interactions. It could be CSA or heteronuclear dipolar couplings. You may ask me what is homonuclear dipolar coupling? That cannot be eliminated by magic angle spinning alone. I will come to that later. Okay, that is not possible to eliminate. It is homogeneous interaction. We will come to that part later. But right now, in the when you are concentrating only in the magic angle spinning, anisotropic interactions, that is chemical shift anisotropy and heteronuclear dipolar couplings are the two parameters which can be eliminated when you start spinning the sample whose spinning speed is greater than the magnitude of the anisotropic interactions. That is, it should be larger than heteronuclear dipolar coupling or larger than CSA. How do you know what is CSA, what is heteronuclear dipolar couplings? You do not know offhand. Keep on increasing the spinning speed till the dipolar, till the side bands disappear. That is what you have to do. So, if you spin at a rate lower than that, you get side bands, they are visible. And as I said, isotropic central band will remain same irrespective of the spinning speed, whereas the side bands start moving away. Okay. So, this is what I wanted to tell you, just to show you an example of a spectrum like this. This is some spectrum of tin 119 CP-MOS spectrum. What is CP-MOS? I do not worry, I will come to that again. I am telling you tin and 119 spectrum of this molecule. This is a static sample, that means no spinning. You see there is a profile of a powder pattern, it looks like a powder pattern, axially asymmetric tensor, you can see that this is CSA pattern. Now start spinning at 3 kilohertz, spinning speed is 3 kilohertz, magic angle spinning speed. Now you have side bands like this, lot of side bands are there. Now increase the spinning speed 5 kilohertz, from 3 to 5, what should happen? The center band should not change at all, that is remaining same. Remember, center band can be anywhere here in the powder pattern, it need not be at the kings as I told you. So, center band is here, that is not changing with the spinning speed. This is your isotropic chemical shift. So, if you want to identify, do at 2 spinning speeds or go to very large spinning speed, remove the side bands. And now what is another interesting thing you must observe, when you remove the spinning side bands by spinning at higher frequencies, you see signal to noise ratio increases here. Look at the signal to noise ratio here, noise ratio compared to the signal light. Look at this noise ratio compared to this. At 5 kilohertz you see signal to noise ratio. There is a enormous increase in signal to noise ratio. The increase in signal to noise ratio becomes better if you go to higher and higher spinning speeds. And this is the spectrum of one of the molecule. Look at it, this is the static sample for spin off nucleus, and you start spinning at 10 kilohertz, this is what the spinning side bands, this is the powder pattern, static case. If you spin at 60 kilohertz, you see the carbon 13 NMR, absolutely no side bands, completely removed, you get only one peak at the isotropic chemical shift position. So, this is what I wanted to tell you, we are removing the side bands, but we can also use side bands. If you get the spin at a lower spinning speed like this 1 kilohertz, 2 kilohertz, you get side bands, we can do curve fitting of these side bands. Then you ask me what do I get? This is a static example of a sample glycine powder. See, this is for C alpha and this is C of carbon. See, both are axial asymmetric tensors, static case. Start spinning, you get side bands. And now, if you go to very high spinning speed, you will remove these things also, and you get only isotropic chemical shifts. If I spin at speed like this 2 kilohertz or 5 kilohertz, I get side bands. I can do the curve fitting. If I do the curve fitting, I also get what is called chemical shift anisotropy, which is useful for me. I can get information of the charge density distribution at the site of the given nucleus. So, CSA can be obtained. So, side bands are also useful. So, what happened is that I am going to, since the time is getting up, I am going to stop here. What I wanted to tell you is today we started discussing about magic angle spinning. I said there are varieties of magic angle spinning rotors are available, which are made up of material called zirconium oxide, silicon nitride, varieties of things are there. Zirconium oxide rotors are commonly utilized, and then put the sample in the rotor of various dimensions 2.5, even 0.7, 1.3, 2.5 like that, varieties of internal diameters are there, rotors, and size of this rotor internal diameter becomes smaller and smaller, spinning speed becomes larger and larger, but at the same time quantity that you are going to use becomes smaller and smaller as the size becomes smaller. These are all things which you have to compromise, arrive at the compromise. And then When you start spinning the sample by keep putting the rotor at an angle with respect to the magnetic field in a probe, and when you start spinning at a larger speed, it is, as I said, dynamic, analogous to dynamic implementation of the cubic symmetry. In other words, consider a cuboid. Different internuclear vectors are making different angles with respect to the magnetic field or one of the axes here. Now, when you start spinning at a rapid speed, all infinite different internuclear vectors making different angles with respect to magnetic field, you can deem it to be aligned along the spinning axis, which is along the body diagonal of the cuboid, which makes 54.7 degree with respect to the magnetic field. This is called magic angle, and I said magic angle eliminates heteronuclear dipolar couplings, chemical sheet anisotropy. These are the very important things, and the spinning speed should be larger than the interaction strength. It should be larger than heteronuclear dipolar couplings, should be larger than chemical shift anisotropy. If it is smaller than that, you get number of side bands. Powder pattern breaks into side bands. Powder pattern is what you are going to get in a static case without spinning. If you start spinning at a lower speed, you have number of side bands. Start spinning at a larger speed, much larger than the interaction strength, you will get only isotropic chemical shifts. If you do not have such a facility to spin at larger speeds, then what you do at 2 or 3 spinning speeds, then the center band will remain at the identical frequency. It will not vary with the spinning frequency, whereas the side bands keep moving away. This is how we can utilize this method to identify the center band. So, I took some of the example to show how spinning speeds will change from the powder pattern we are going to get sharp peaks, and how the signal ionization increases and everything. And I also said sometimes the side bands at lower spinning speed are useful. Use it, do the curve fitting, you can get CSA values which are useful. We throw information on charge density distribution at the site of the given nucleus. These are what we discussed. We will come back in the next class and discuss further from this point. Thank you very much. I will stop here.